So next we're going to go to our viral box in order to create a packet capture. So we web browse to whatever the machine is. Okay, in this case mine is running in the cloud on packet.net, packet.com. And we're going to go down under interfaces and we're going to create a traffic capture. So like I said, I want to capture on router 2 and XR2. So I'm going to check router 2, gig 2, and we're going to traffic capture. Okay, everything else leave as default, just create. Then likewise, we're going to go down again under interfaces. I need to expand this. We're going to go down to XR2. Its interface connected to the virtual switch is gig Ethernet 0000. So we check this one, and then traffic capture. Okay, create the capture. Now we're good to go. Okay, under My Simulations, under the simulation, and now under traffic captures, we should see that both of these are running, is true. Okay, next step is we're going to generate flows. So the ultimate goal here is we want IP reachability between router 6 and router 7. We already established that per just the basic topology. You load up this config, I already have it solved. So the point of this is that you don't need to build it, you can just look at the working example, right? Okay, working example here was that we go to router 6, we look at the route to the other site, so show IP route 7777, or just show IP route, and we see that we do have reachability, inter-area reachability to someone that's on the other end of MPLS. So specifically, router 6 is saying I could load balance either to 4 or 5. Packet gets to router 4. Router 4 says, how do I get to show IP route 7777? It says go to 10.4.11.11 on interface gig 2.4.11. Okay, gig 2.4.11 is sending us towards the provider edge. So in other words, any IP packet that router 6 sends that is going to 7777 that lands on router 4 is going to send it that way. Okay, likewise, router 6 said, well, I had an alternate path. I could also go to router 5. We go to router 5 and we show IP route 7777. It says my next hop interface exit is gig 2.15, okay, which is going towards router 1. At this point, the key is if we were to do a packet capture, this would be just a regular IP packet. So if we're web browsing, it would be our web data, encapsulated inside of TCP, encapsulated inside of IP, and then directly onto Ethernet. Point being, there is not yet an overlay tunnel when router 4 or 5 forwards this packet out to the provider. It's just an IP packet. Okay, now it's up to the provider edge to tunnel it. The goal here is that we're trying to tunnel a packet between router 1 and router 3, or 1 and XR3, okay, any of those edge routers, because the final problem at the end of the day is that router 2 and XR2, who are in the core of the network, they do not know the route to get to 6666 or 7777, ultimately the customer network. So if we were to create a regular IP packet going from router 6 to 7, this lands on router 2. Router 2 says, hey, I don't have that route. So either we fall back to a default, the packet is misrouted, or we have no match and we end up in a traffic black hole. In either case, though, packet's not getting where it's supposed to, because router 2 doesn't need to know that route in this design. Instead, the only thing router 2 needs to do is how do I label switch traffic between the edges? Okay, the easiest way for us to see this is to look at this from the data plane. Okay, so on router 6, we're just going to do a ping. Okay, ping to 7777. Source is 6666. And let's now look at this from our packet capture point of view. So if we go back to viral, we're going to go to router 2's capture. We're going to download this. Okay, the little zip button there. That open in another window in my download manager. And then let me open up the zip file. And inside the zip file is your packet capture. So if you have Wireshark installed, then it already is going to just default to this. Okay, so notice what's running in the control plane behind the scenes to begin with. Okay, we're running OSPF, both version 2 and version 3. We should be able to see that because we have two different layer 3 transports, right? Destination 224005, that's OSPF version 2. Destination FF02::5, that is OSPF version 3. Likewise, we're running EIGRP version 6, FF02::A. That would be the IPv4 equivalent of 224.0.0.10. We have LDP. LDP is multicasting to UDP port 646.224.0.0.2, which is all routers. And then BGP, of course, is using TCP unicast at TCP port 179 in order to exchange the information directly between the boxes. Okay, someone is also running ISIS routing, but notice that ISIS routing is encapsulated directly inside of Ethernet. We have the ISO ISIS payload inside LLC inside of Ethernet. Or in other words, IS to IS is not an IP protocol, it is its own protocol stack. It is part of CLNS or CLNP. Different from OSPF, which OSPF is IP protocol number what? Okay, before I open it, do you guys know this? 80 what? IP protocol number 89 is OSPF IGP. So OSPF is using IP for transport as opposed to its own protocol, like ISIS is using. Okay, likewise, LDP is not using its own protocol. It's using protocol number 17 for transport. It's using UDP. We would also see LDP that is unicast LDP, which is for actually exchanging the label information. This would be using not UDP for transport, but this would be using TCP. So if we search for LDP, okay, let's go to the display filter, just type LDP, enter. And we should see that at least some of these packets would have been generated by TCP, okay, which is this one. This is a keep alive message going from router 1 to router 12.12.12.12, who in our case 12.12.12.12 is XR2. Okay, so this means that this is the LDP hello message going on this link between router 1 and XR2. Okay, but remember the traffic capture that I did. Traffic capture I did was on router 2's segment. This is a function of the virtualization. The virtual switch is technically running in promiscuous mode. It's acting like a hub. This is what makes this topology easier to learn on. It means that you can do a packet capture anywhere. It doesn't matter. Packet capture on any segment attached to the virtual switch and you will see all frames. You'll see them pre-IP encapsulated and you'll see them post-MPLS encapsulated. So when we look at the ping here, it's going to be capturing everything. And we're not capturing just on an individual link like gig 212, we're capturing on the virtual switch. Okay, if we go back to the VM Maestro topology, this would give you more information about that. That really what's happening is that XR2 and router 2, they're connected to unmanaged switch 1. That's where the packet capture is really happening. So everything going in and out of this switch is being written to disk. That's why I'm seeing frames going to XR2 when I really wasn't theoretically capturing on that link. I really was. Okay, so point being, if we now go all the way down to the bottom and we search for our pings, let's look for ICMP, we should see these encapsulated a couple different ways. Okay, we may see it coming all the way from the edge as just a regular native IP packet. We may see it coming multiple times in the core. This is just because of the virtual switch, but notice that we see it MPLS encapsulated. Okay, so let's take this first one here. We have an ICMP ping, an echo request, that's going from 6666 to 7777. Okay, inside the actual ping, that's the request. We don't care about the data. This is just going to be like garbage, ABCD. What do we care about here is the Mpls label. Okay, it says that there's two label numbers. We have label number 17 and we have label number 18. But we need to think about how does the router actually read this? Is it reading it left to right? Is it reading it right to left? Okay, I posted a joke the other day on Twitter about something called Big Endian versus Little Endian. That's actually a real thing. That historically, some protocols did go left to right, some protocols went right to left, caused all sorts of issues. Okay, today's that's not an issue. You read this top down. So what I mean is that when the router is actually processing the frame, you would look at it as if it's coming in first from Ethernet. What's the Ethernet processing that happens? Once Ethernet is done, then you go down to the next layer, which is MPLS. This is the first label that the router would be processing. Okay, so we now need to know who is the layer 2 hop with this MAC address that has label number 17 bound to something. Okay, well, we know where the ping was coming from, right? The ping was coming from router 6. It's either going to 4 or 5. We were capturing it on router 2, so hopefully we're looking at the frame that came this way, right? So let's look at this from router 1's point of view. On router 1, I want to know what was the label that we associated with that final destination, 7777. A couple different ways I can see this, by simply looking at show MPLS forwarding table, or we could look at the hardware entries. Show Ceph for the VRF, B as in Brian. Show Ceph what? Show Ceph detail maybe first. Show Ceph IPv4. Okay, syntax is a little bit hard to guess it here because I need to show the VRF aware process. Let's try show IPseph. For the VRF is B, and then the entry is 7777/32. Show me the detail. That's what I need to see. Okay, what this tells me from router 1 is that we do have an exact match. Okay, we know how to reach 7777/32. It recursed, it searched for the next hop, it found the next hop was 3333. We found a label for that was number 18. But really, to get to 3333, there's multiple places that we could use. From router 1's perspective, we could either go to router 2 on interface gig 2.12 with label number 17, or we could go up to XR2 to the upper right from router 1, and in that case we would be using label number 24002. Now the key here though is that notice that there are multiple labels. We have label number 18, we would consider this to be our VPN label. Then we have the label at the bottom, number 17, we would consider this to be the transport label. This is what we ultimately saw in the data plane. Data plane says we have two labels that encapsulated this packet. Label number 17 on the outside and label number 18 in the inside, the VPN label. Okay, so why are we even talking about this, Brian? This has to do with segment routing. When we're doing segment routing, what we're really changing is the outer label. We're changing just the transport label. What we do not need to modify is anything that's going on in the PE related to the actual MPLS layer 3 VPN, layer 2 VPN, or whatever other protocol that you're running. So what that means is that this is a non-disruptive upgrade. That's great, right? You can run half of the network with LDP, RSVP-TE, BGP, whatever design that you currently have, and you don't have to go greenfield. You can do a brownfield migration where part of the network is now running segment routing. We leave the segment routing portion and get onto the LDP LSP. There's no difference. Because from a data plane point of view, the only thing we're ultimately doing is adding a label on top of the payload. Payload is Ethernet, payload is IPv4, IPv6, we don't really care. Okay, down the road, we'll talk more about IPv6 and how does segment routing interact with that. That's NGN. That is what is, not LTE, that is what is 5G. 5G means segment routing from a marketing point of view. We'll talk about that in more detail later. Okay, so we know now what does the data plane look like. Okay, we said the data plane was your IP packet, plus it was these label numbers. Next thing we need to talk about is the control plane. So yes, ping is working. Customer is not calling us saying, hey, I have an outage. Everything is working. Now we want to make some sort of change about how was the network signaled. Okay, this is the control plane. Okay, so let's go ahead and take a 5-minute break. And then when we come back, we're going to get into our next section, which is to look at the difference between LDP and segment routing. How are they doing the actual label distribution? So quick 5, and then we will continue from there, guys.